Hi everyone, my name is Glenn Govender, and today we're going to be looking at fusion reactor technology as part of a capstone project for Thomas Edison State University. So as many of you know, fusion is something that's already occurring in our solar system. It's just happening light years away. Are the discovery of fusion and a brief history of fusion experiments, the fusion process, the current crop of test reactors that are being utilized to experiment with this hopefully up-and-coming technology, and the benefits and necessity of fusion, where it stands in our global economy, and really the importance of harnessing this new tech. And then a brief summary of what we've covered. So the first question, who do we have attributed to discovering fusion? Well, there are two scientists that come to mind, and they are Atkinson and Hooterman, and it was 1929, and they discovered fusion by going through Einstein's theory of relativity. Now, given the technology at the time, even having discovered this new possible form of energy, they really didn't have the capability to test anything. So, it wasn't until 1951 that fusion research really started to take off. And it wasn't in the benefit of mankind. Well, maybe it was, but that's one of those things that's debatable. It was a weapons test. And the weapons test was called Operation Greenhouse Item. Now, this weapons test consisted of 4 different weapons being used. From the image, you can see that they are nuclear in nature. Now, while most of the weapons at the time that were nuclear were fission-based weapons, there was a test subject. So how did we test fusion in this weapon? Well, they decided to use deuterium-tritium gas as a booster agent in this fission-based weapon. Now, while not being solely a thermonuclear device, this gas did provide enough of a boost to the fission process that while the weapon initially might have had a yield of 25.5 kilotons, as did the other weapons in this test, uh, with the uh, with the booster agent applied, it actually saw a 45.5 kiloton yield. Now, that is almost double the other fission-based weapon. Now, while weapons testing was the initial stage of fusion research, uh, the in the UK in 1958, um, we began testing fusion as a means of power production. So the first experimental fusion reactor, Zeta, was the first large-scale device tested, and it was in the UK. And some of these are the headlines of the day: Son of Our Own, the Mighty Zeta, and every news station and every news article at that time was uh, hugely impressed by the scientists that had come up with this, homegrown sun essentially. Um, it used a Z-pinch type containment system. Now, while the Z-pinch type containment system is no longer used in its initial state, it does go on to be modified and actually has a huge part to play in the development of the tokamak um, containment system, which is the current containment system most commonly used in fusion reactors, which we will go into more detail later on. Now, while Zeta might have been the first fusion reactor to be built on a large scale and tested, specifically using the Z-pinch, or what will be later to become the tokamak style type of magnetic containment system, at the Princeton Plasma Physics Laboratory, another style reactor was being used in order to test fusion reactors and various ways to contain the plasma that was generated inside of them. It is a stellarator type design. Now, while a stellarator type design is similar to the tokamak, it does have some key differences. Now, while it still contains the torus shape, it still uses magnetic containment, it does not put a plasma current through um, the superheated plasma inside the reactor. Now, instead of doing that, it uses a set of magnets that are actually twisted out from each other. So there is a helical shape to the the magnets that are part of this torus-shaped donut. So it does not put a plasma current through. Now, the importance of not putting this plasma current through is the instability added by applying this additional current, even though it does add quite a bit of added containment to the system. Now, initially, the stellarator design posed some design issues. The complexity of the magnet arrangement in this helical shape um, added expense and time. Now, as the currents in these reactors have started to go up, the tokamak design is proving that, well, there's some issues. So the stellarator has actually seen some renewed interest recently. Now, we've talked about the tokamak design, and we briefly discussed the stellarator design as well. Now, the tokamak design came around in 1968. It was developed by a group of Russian scientists. Now, the design utilizes magnetic fields in a vacuum to contain the superheated plasma. Now, the magnets also are there to squeeze the plasma, and this squeeze or pinch uh, helps the fusion process to take place. Now, as part of the design, unlike the stellarator, we do use a current running through the plasma. However, unlike Zeta, the plasma current was actually lowered in order to maintain stability. Now in the design you can see that there are multiple magnets being used here. We have a toroidal magnetic field, the interpoloidal magnetic field coils. You can see the coil current and outer poroidal magnetic field coils as well. Your plasma is being routed through this toroid shape. Now the toroid shape is so that you can maintain the direction of the plasma. If it was a straight line, you would have issues with leakage at the end, because once the plasma hits the wall, you're going to lose your heat. You're going to have to basically revert to your initial state and start over. Now the next major breakthrough as far as fusion reactors took place in Japan. The JT60, the Japan Torus 60, it began operation in 1985, and it is also a tokamak reactor. Like I said, this design became very popular given the simplicity that was present in the design at the time. It also, this reactor holds the record for the highest triple fusion product achieved in any test reactor. This record still stands currently today. Now, the triple fusion product. In order to achieve fusion, three things must be present in sufficient quantities, as stated by the physicist John D. Lawson in 1955. Now, you're talking density of your nuclei. You have to have enough heat present. Now, heat ranging, the sun's temperatures are roughly 15 million degrees Celsius. In order to achieve the same type of fusion reaction that occurs in the sun on Earth, we actually have to achieve temperatures far greater, roughly 10 times greater. We shoot for between 150 to 200 million degrees Celsius in order to have enough heat to create a fusion reaction or start a fusion reaction. And the third part of the triple fusion product is a long enough period of confinement. Now, in order to have a long enough period of confinement, you have to have a stable confinement. So, magnetic confinement is what we've been using based on the fact that we don't have the materials present, or the materials were not present to be able to handle temperatures of 150 million, which is another reason that the magnetic confinement is so popular when it comes to reactor design. Now, while the Japanese were working on the JT60, we had a joint European Torus project, which goes by the name of JET, and it is a reactor still currently being used in testing. Now, this reactor started up in 1983, so a couple years prior to the Japanese, but it did not achieve anything considerable until after the Japanese reactor already came online. It's located in Oxfordshire, and it also is a tokamak containment system. Again, very popular based on the simplicity of the design. Now, the first plasma was achieved in June 25th, 1983. Now, it was a fraction of a second, a fraction of a millisecond, in fact. And really, there was no uh, uh, measurable power output achieved when this plasma was created. Now, 1991 marked the first fusion power release during a tritium experiment. Now, deuterium and tritium are the two isotopes that are most commonly used and are the goal isotopes to be used for fusion power. Now, 1997, JET set a record. 16 megawatts of power were produced from a 24 megawatt input, and it is currently the world record for fusion power production, and that record has not changed as of yet. Now, therein lies the problem with fusion power currently, is that we have yet to achieve a net power gain. Currently, it takes more power to start, maintain, contain the fusion process than we actually see released. Now, having gone over the history of fusion and some of its key moments, we're going to start looking at the fusion process and what actually takes place or needs to take place in order to create fusion energy. Now, the two isotopes being used are deuterium and tritium. Now, when they fuse together, they form helium. Now, once that happens, you have a neutron released and an incredible amount of energy. So, what needs to take place in order for that to happen? We need high temperatures, as I stated earlier. Now, again, based on the fact that we do not have the gravity of the sun also forcing these two isotopes together and keeping the energy contained, we would actually have to create temperatures in excess of the 15 million Celsius and shoot for more 150 plus million Celsius. That is to overcome the electrostatic force of repulsion present in the nuclei. Now, you have to bring them close enough together to allow the nuclear force to overcome the electrostatic force in order to force a fusion to occur. You heat the atom past its point of ionization energy. Its electrons are stripped away. The heated gas, no plasma is conductive, and can be controlled via the use of magnetism. This process allows almost any nuclei to be used. However, lighter elements are more easily controlled and require less input power to force a reaction. Now, that is the reason currently that we are experimenting so heavily with deuterium and tritium. Now, having gone over the fusion process and the basics that go into a fusion reaction, we're going to start talking about the current crop of test reactors and some of the key points that go along with each of these devices and what direction it looks like the companies are going with each of these to differentiate them from the other reactors that are also in play. One of the current test reactors being produced is being produced by Lockheed Martin's Skunk Works division. It is Colicium, and it is a small fusion reactor, at least in comparison to the current crop of fusion reactors. Now, they have written a couple articles about this reactor, and they have brought up how it is something that could be the size of a dump truck or a pickup truck instead of the size of a building. Now, they haven't released any solid numbers yet as far as power output or what their goals are with this reactor, It seems like miniaturization is really the key here as far as creating a reactor that could be used in more than just a large-scale energy production need. Um, the next is the Burnaby fusion reactor, and now this is a innovative hybrid design reactor. Uh, the key with this from General Fusion is using existing technologies instead of very expensive magnetic containment systems or um, inertial containment systems utilizing lasers and other ways in which to contain the plasma being created on the inside of this reactor. Now, this uses a molten lead lithium used as the heat transfer medium, and as you can see in the photo here, it has a number of rams and positioned around the outside of this sphere. Now, these rams are used to accelerate the pistons to speeds capable strong enough to send shock waves into the heated plasma to create the fusion conditions needed. Um, The next reactor is the W7X German reactor. It is one of the few reactors still using a stellarator design. This has been made possible through the use of supercomputers to design each of the 6-ton magnets that are around the toroid shape of this reactor. The goal with this reactor is a sustained hydrogen plasma, and they were able to create this sustained plasma for a few milliseconds during a test in February of 2016. Now, without the plasma current, again, that stellarator type design does have its benefits over that original tokamak design, and could be used in longer or over longer periods of time instead of in pulses. The next reactor is the Chinese Fusion Reactor East. Now, it is a tokamak containment system reactor, tried and true. Now, was able to sustain temperatures of 90 million degrees Celsius, and a plasma was sustained for 90 seconds. This reactor has been in operation since 2006. The most recent test was conducted in February as well, um, and the results of this were actually released right after the W7X German reactor. And lastly, we have ITER. Now, ITER is the largest construction effort as far as a fusion reactor goes. It is a 35-nation joint collaboration effort. Um, it has 10 times the plasma chamber volume of the current largest fusion test reactor, JET, and it is going to be, assuming that the their goals are met, it'll be the first fusion reactor to have a net power output. The goal output is 500 megawatts, and that would be with a 50 megawatt input. Um, and the other goal with ITER is a plan to use it as a tritium breeding testbed. Now, while deuterium can be extracted from salt water, tritium, on the other hand, has to be created. Now, in a fission reactor, it is a byproduct, whereas in a fusion reactor, it is not. So, in order to have the tritium or create the tritium that we would need, a lithium blanket is being utilized outside of ITER, and it is utilizing that lithium blanket to create the tritium and feed it back into the reactor to go along with the deuterium to um, cause our fusion and hopefully generate our net power output. Having gone over some of the test reactors, the fusion process, now let's talk about the benefits of fusion power. Um, Fusion is a naturally clean, no greenhouse gas emitting uh, form of nuclear energy, form of energy production in general. Now, the only thing that stays irradiated in a fusion reactor would be the core, and that would be for roughly 100 years. Um, Now, we do have an abundance of fuel if you take into account that deuterium can be pulled from seawater and that tritium can be bred. Uh, like I mentioned during the discussion about ITER, that would be utilizing a lithium blanket in the reactor itself. Um, with fusion, we are not concerned about control rods. We have no need for them. Um, when a fusion reaction needs to shut down, we simply remove power, and it cannot sustain itself any longer. There is no real waste with fusion power. And of course, the goal is power production. Well, fusion theoretically has a much higher output from a sustained fusion reaction than nearly any other form of uh, energy generation that is currently available to us. So why is it important? Um, Fusion is important to our future because of a number of factors, some of which include the growth in the world's populations. As we keep expanding, as we keep demanding more energy, we have more electronic devices, we are going to need more power. The World Energy Outlook of 2014 says that we will approximately need 7,200 gigawatts of capacity to keep up with demand by 2040. To go along with that, 40% of our current power plants will be retired by 2040. Um, so in order to continue our current power production and to improve upon it, we are going to have to come up with um, something to replace those power plants that are going to be taken out of service. A diversified power portfolio is something that's looked at as far as a concern for national security, for global economies, and not only is that portfolio important for the economy, it is also going to be important in our reduction of carbon emissions and greenhouse gases. Nuclear energy and fusion in particular could provide a huge boost to our conservation efforts of our um, clean air and things of that nature. Uh, and to top that, in developing nations that are currently lacking a reliable form of energy, fusion power could be just the thing that many of these nations need to have a reliable electric grid. Some of the energy consumption figures from the World Energy Institute projecting the number of BTUs that are going to be required to maintain our current lifestyle. So having spoken about the benefits and the importance of fusion power, that concludes this presentation. Now, the things we covered the fusion process, the actual way in which fusion power is created. We covered some of the test reactors to include ITER, W7X, the German reactor, and EAST, the Chinese reactor that currently holds the record for plasma at 90 seconds sustained. We also covered a brief history of fusion and some of the important moments in fusion power, including some of the early tests, which unfortunately were weapons-based, but they have gotten us to the point we are now where we can really start looking at fusion power as a way of power production. Thank you for watching, and look forward to any comments and input.